Here I'll discuss how Siemens can provide pre-built whole car kinematic simulations that not only include elements of the suspension such as the chassis and tire models, but also aspects like the powertrain. This can then be applied to custom lap time simulations. Then touch on how we can help further lightweight your vehicles through the application of more realistic, dynamic structural simulations and topology optimization. Some common issues teams run into when using software for suspension design is the kinematic software is difficult to obtain or learn. Or they may use software to write equations to compute the kinematics, and this takes a very long time to do. It risks not being adopted by newer generations of teammates and usually makes assumptions which is prone to error. The lap time simulation software may use a simple point mass approximation which lacks accuracy. And the software used only handles suspension kinematics and cannot be applied to lap time simulations. That brings me to Simcenter Aimsim, which is a system simulation platform that can be easily coupled to major CAE, CAD, and control software packages, can interpolate with the functional mockup interface, Modelica, and connect with other Simcenter solutions as well. First, consider that there are 6 video tutorials showing how to use Aimsim to design a suspension system, specifically for a Formula SAE car, and run lap time simulations. Here's a short 3-minute clip that takes snippets from those videos to illustrate how you can apply this to your car. These videos start by highlighting detailed suspension modeling in the software. At the end of that video, it highlights importing tire data, which brings me to Simcenter Tire, where the goal is to represent tire forces in moments throughout the vehicle dynamic simulations. Simcenter Tire consists of a tire measurement service through the tire test trailer on real roads. For student teams, you can get this data from other sources such as tire consortiums. The tire testing results are processed to the standardized TIDEX format, which serves as an input for the parameter identification. Then parameter identification is performed with MFTool from the tire testing results. MFTool allows you to easily identify the tire model parameters from the measurement data, then manipulate and visualize the tire model characteristics in an efficient and user-friendly way. This enables fitting of the curve in historic tire models, database and plotting functionality, and the ability to let the software make estimates where needed. The output of MFTool is a tire property file that can be read by MFTire and MFSwift to model the tire, which can be coupled to a large variety of vehicle dynamic simulation packages. MFTire is a magic formula-based tire model that can be used for vehicle handling simulations and can account for pressure dependency and nonlinear relaxation length. MFSwift is also available, but teams primarily would be focused on MFTire as it's used for handling. Some things that should be included in your models is transient tire behavior. For example, when shear input is applied, like in the case shown here, where 1 degree is applied, the tire needs to build up deformation before a steady state level of force is obtained. Knowing there is a transient behavior, you can estimate the effect using a mathematical filter which can still give you a nonlinear transition to the point of saturation. We, however, measure the nonlinear transient behavior during test and use that to generate a physical model that predicts the nonlinear response at the tire contact patch. Let's take an example of steering correction in a corner. Our physical model can give a more accurate representation of the tire response, as the linear filter can only perform the same function as it did before the steering correction. Tire temperature and forward velocity has a significant impact on things like cornering stiffness, peak lateral friction, and more, and therefore affects the overall vehicle performance. We've developed a module which models this in a computationally efficient way that is directly available in all relevant vehicle dynamic simulation products. Applying simulations like suspension simulation in Simcenter Aimsim, which runs very quickly, to an automated design space exploration study with HEEDS enables you to explore hundreds of design scenarios and optimize a system. In this particular example, they are focused on the induced toe angle during a bump maneuver and the self-steering angle during a steering maneuver. To understand what HEEDS is, though, the software allows you to automate data sharing seamlessly between a wide variety of various tools in case you need to involve them in the study. This illustrates some of the tools it can couple with, which includes the ability to work with software developed in-house. HEEDS manages your computer resources to speed up the automated explorations. It uses efficient search technology to seek out design objectives and learn about the design space, and saves you from the massive time investment of needing to manually record data and plan how to plot everything, since it allows you to reach into everything it's found to make your own plots, tables, and more whenever you need it. But back to the problem. When using 3 cores on a Windows laptop, in 2.5 hours, 300 design concepts were automatically explored by varying 6 design parameters, such as the X, Y, Z hardpoint locations of the upper and lower spindle ends. The trade-off between the 2 objectives was smaller than expected, leading to a better understanding of the design space and the problem posed. HEEDS reduced the induced toe angle during the bump maneuver by 65% and reduced the self-steering angle during the steering maneuver by 99% compared to the starting design. They discovered relationships between the performance metrics which can be exploited in further development. Here the feasible designs found during the search are shown in blue, and the red show the best designs found. The best designs show that the higher values in most variables are needed. Only OKZ takes values on the lower end of its range. For 3 of the variables, the best designs lie against the upper limit, so it's likely that better designs could be found if the limits could be increased. The ranges on the variables give an indication to the allowable range for a given variable to produce designs with the preferred result. This can be useful in making decisions related to the reliability in manufacturing and system performance tolerances. 3D bubble charts provide additional insight into the design space. When looking at the 3 variables shown, X, Y, and Z of the lower spindle end, most of the high-performing designs are found in the indicated corner of the design space. These relationships between the performance metrics were discovered through the search and can be exploited in further development. Pratt & Miller shows how this was applied to develop a new tactical military vehicle in 14 weeks. There were 40 constraints on the vehicle performance involving maximum vertical and lateral accelerations, yaw and roll overshoot, absorbed power, ride frequencies and damping, and overshoot. Additionally, there were 44 design variables, including spring rates, damper data, geometry, and roll bar attributes. They built a validated car model of the vehicle, and to find a suitable design, they used response surface methods, but after 12 weeks, they couldn't find a single feasible design. They switched over to using heat, and within the first 200 evaluations, they discovered 61 feasible designs and identified the optimal design after 123 evaluations. Here is what that vehicle looks like.
That's the best vehicle I've ever ridden in. After I've been an infantry battalion commander, served in the Army for 25 years, ridden in the Jeep, the Humvee, tanks and Bradleys and trucks. And this is exactly what the warfighter needs.
Hayes also helped 888 Race Engineering and the MGKX Momentum Racing team achieve a first-place finish and season opener at Brands Hatch by minimizing lap time through improving the front and rear springs and anti-roll bar options.
And he's victorious at round 3 of the British Touring Car Championship. What a feeling that must be for Plato. Victorious ahead.
Many auto racing teams already use simulation and design exploration software to help them optimize the setup of their vehicles, improve cornering ability, and minimize lap time. And while this traditional process has dramatically improved vehicle performance and competitiveness, it also sometimes leads to vehicle designs that are challenging to drive. To address this, 888 Racing performed a design study that considered the drivability of the car, measured by steering power, and lap time along with the 39 suspension and driving parameters and 5 static and dynamic load cases. This study yielded a trend of the best design trade-offs for lap time and drivability. Engineers then selected a design that represented the best compromise rather than the lowest lap time. In the process, they also determined that there were some curbs on the course for the driver to drive over, whereas there were other curbs to avoid completely. This approach helped them to achieve 4 pole positions and 12 first or second place finishes during the race season. Another common issue is that student teams cannot lightweight as much as they would like because they cannot account for how forces apply to components in motion, so they rely on assumptions for the loading conditions for a static FEA case and then compensate with a large factor of safety, which leads to overbuilt parts. They also cannot leverage 3D printing to its fullest. With Simcenter 3D, you can perform these types of simulations directly in NX or use it in a combination with a variety of other CAD platforms, which is especially useful since this enables fast design iterations. This enables structural, acoustics, flow, thermal, motion, and composite analysis, as well as optimization and multi-physics simulations. It's noteworthy that this uses the long-standing and trusted Nastran solver, or you can use the simulation capabilities within Solid Edge, which are shown here. In either case, you can run a motion analysis of your suspension and track forces on a component, in this case the upright, and then apply a selected set of forces from the motion analysis to FEA, all within one platform. It's noteworthy that there are e-learning courses that show you how to do this. Or you can use a 4-post shaker motion simulation that uses road load data and multi-body simulations to apply motion loads to your suspension, and from this understand the strength and durability of your system. Again, keep in mind that this is directly connected to the CAD, so making changes and running new simulations is very easy to do. Using simulation, we can evaluate the performance of the system and capture the requirements down to the system components. Then the requirements can be fed into design optimization, where the function is driving the design. If your team can't print organic shapes like what is shown in this example and needs to rely on traditional subtractive methods, then different design constraints can be used to develop a part you can manufacture. For example, extrude along a vector is useful for a part that needs to be made using a 2.5 axis machine. If you are able to 3D print your part of interest, integrated lightweight structure design capabilities make it possible to perform an optimization that can recommend areas where further lightweighting can be realized. Heats can be used to consider all relevant load cases, materials, mounting options, manufacturing type, and more to look into conflicting requirements. Then you can validate the design in the context of the system by swapping out the old part with a new one and rerunning the simulation. The design can be further refined. In this example, our surfacing technology is being used to create more structural elements. The design can be validated for manufacturing so that the users can look at the representation of the area overhanging angle for additive supports, check for material inclusions, minimum wall thickness, and the layout definition for the building tray. Then 3D print preparations can be made to look at the print job setup by selecting the printer and the build tray, positioning and nesting of parts, creating the associative support structures for metal parts using powder bed fusion methods, and the different build processors generate the output to drive the selected 3D printer with the right parameters for the material and print strategy. It should also be considered that in addition to topology optimization, also known as generative design, that CAD parameters can be used to perform a parametric design space exploration study to achieve a design objective. In this case, 2 CAD dimensions were changed and a goal was set to keep the maximum stress less than or equal to 2000 psi. And within 5 automated iterations, the weight was reduced by 1.5 pounds while keeping the original constraints. To learn our software, we have libraries for Aimsim with pre-built systems such as clutches, torque converters, and more in the Aimsim interface under Demo and Help. This is available in combination with the 6-part YouTube tutorials that were shown earlier and these e-learning courses. There are e-learning courses on frames and weldments, topology optimization, and finally, motion, FEA, and mechanisms. Each of these products are supported by documentation, tutorials, getting started guides, and more by the resources in the Support Center. To review, I covered how we provide software that will save you time, increase the fidelity and scope of your simulations, and further lightweight your vehicles through the use of pre-built whole car kinematic simulations that include the suspension, chassis, powertrain, and tire models, lap time simulations, realistic dynamic structural simulations, and topology optimization.